So, we continue looking at optimization, and we are looking at methods which we call as population based. So, basically when we say population based methods, and we will spend some time on this today, we mean that instead of working with a single candidate solution, for example, as we do in hill climbing or in simulated annealing, we work with a population of candidates. Okay. Now, the benefits that we get by working with populations are not just speed up, because it is not as if you are running the same algorithm k times or n times if n is the size of the population. You also get benefit from the fact that different candidates can contribute jointly to exploring new solutions. Okay. So, essentially we are exploring the solution space, which for real problems may not be a smooth surface, and we are looking for methods which would be robust, which even when the terrain is jagged will do reasonably well essentially. So, in population based methods, the method that we are looking at this moment, we have called it as genetic algorithms. Some people also call them as evolutionary algorithms. And they have a flavor of bottom up problem solving. We also call as emergent. So, by emergent systems we mean that we put together a collection of simple elements and more complex behavior emerges out of that. And as we might have said before, the human brain is a perfect example of that. Every neuron in our brain is computationally a simple device, but it is just that we have billions of them in our head, and they are, it is a connections, it is the way that they are connected to each other that really gives rise to our individual brains essentially. So, the idea in genetic algorithms is that we have candidate solutions rather a population of candidate solutions, and each candidate is made up of components. So, you can think of this some kind of a breakup of every component. Now, in the simple case that we saw about solving SAT, every component is the value of one variable or one bit, and a SAT solution candidate is a bit vector. But in general problems may be more complex and components may themselves be more complex in nature essentially. In which case of course, you have to be careful, because the general strategy in solution space search or perturbation search that we are exploring is that we perturb candidates to produce new candidates. So, if we had this as a candidate, then simulated annealing might try to generate a neighborhood around this by changing one or two components as we saw in the case of SAT and do that. So, one has to do that a little bit more carefully essentially. So, when we talk about genetic algorithms, we have to talk about encoding a candidate solution as a string. In terms of genetic algorithms, we would call this as a chromosome, borrowing from the biological world, and essentially there is an interplay between chromosomes of different parents essentially, which basically modifies the design of the candidate or design of the solution essentially. So, we had mentioned in the last class that there are these two things, one is the genotype which is made up of the genes, and that influences or that decides the behavior of the phenotype, which is the individual or the creature or whatever is participating in the real world essentially. So, in genotype we look at recombinations, and the phenotype basically competes and it participates in selection. So, these are the two main components of the problem solving strategy that you might say nature employs, which is a trial and error with its designs, and the design is expressed as a chromosome essentially, which is some kind of a string that we are going to work with, and we say use the word recombinations. So, the idea in genetic algorithms is that you draw some components from one parent, some components from another parent, and in the hope that you will inherit the good components of both parents. So, if you going back to the rabbit and fox's example, let us say there are two desirable properties amongst rabbits. One is that they can run fast and the other is that they are smart. So, whatever that means, So, for example, you must have as a child heard the story about the rabbit who has to go to the lion in the jungle as food, and then he is a smart rabbit and he tells the lion of another lion and that kind of stuff. So, either they are fast or they are smart essentially, which is contributes to their survival. So, the whole idea of evolution is that in a population of candidates, the phenotypes, the fitter ones are the ones who survive the competition. The competition is for resources, it could be for food, it could be for mates, it could be for shelter, which is safety from the predator essentially. So, if you are good at doing these things, then you are likely to survive, which means you are likely to pass on your genes to the next generation and so on and so forth. Now, imagine two parents of a rabbit, one of them is smart and the other one is fast essentially. The hope in genetic algorithms is that if these two parents have, let us say, two children, that is the model that we are following here, at least one of them will inherit both these properties of being smart and being fast at the same time, which means it will be like a super rabbit essentially, right, and super rabbits will give rise to more super rabbits and so on. So, in general the rabbit population will become smarter and faster essentially. So, that is the whole idea behind genetic algorithms. Like we said, one makes up the combinations. So, there is one process or one force which makes up the combinations, churns the genetic pool, and the other which is the process of selection, which is that they compete for survival essentially. So, survival of the fittest, and when we say survival of the fittest, at least in the case of genetic algorithms, we are going to impose a fitness function on top of the algorithm, because it is based on the fitness function that the candidate will survive. But in the real world it is the other way around, it is basically whoever survives is the one who is fit essentially. So, I want to do one example of to illustrate genetic algorithms today, but before that I want to sort of spend a few minutes on this idea of emergent systems essentially, because it is an idea which is has a lot of followers essentially. So, you must have heard about this Conway's game of life. Conway, something called game of life. Have you heard about the game of life? It is like a screensaver sometimes, and the world is a grid in cellular automata. So, you have rows and columns and so on. And in the simplest form of this game, in every cell. So, every square is a cell inside, there can be one creature, and the creature is a very simple creature. It survives. So, it has some rules for survival. There are rules for surviving, there are rules for being born, even in this very simple world there are rules for dying essentially. So, the simple rules in this Conway's game of life are that if you are surrounded by more than 3 living cells or creatures in living in cells, then you are sort of overcrowded and you die essentially, which means that each cell is in a state of 1 or 0. 1 means it is alive and 0 means it is dead, or the creature inside is dead. So, if there is a 1 surrounded by more than 3 ones, then it dies, it becomes a 0. If a 0 is surrounded by exactly 3 ones, then it comes alive, and if a 1 is surrounded by less than 3 ones, then it stays alive essentially, or something that I may have a small error there, but anyway, so something of that nature. So, you have this very simple rules which control how a cell evolves over time. So, it is an automata which goes through a sequence of time steps. So, at every time step, every cell decides whether in the next time step it will be alive or dead or whatever. Now, it turns out that this very simple rules of life, if you want to call it life, gives rise to patterns in this world, which is a grid world, which have a tendency to survive, and some patterns survive, some patterns oscillate between 2-3 patterns, and some patterns even move forward. So, if I remember correctly, there is a pattern which looks like this, that if this is 1 and this is 1 and this is 1. So, these 5 patterns, if they are 1, and maybe you should try the rules that I just mentioned on these cells, then this pattern essentially in the next cycle will move a little bit to the right, maybe it will rotate by a little bit, and it will keep doing that. So, as the time progresses, this pattern will appear to be moving in this direction. Now, this should sort of takes me back a little bit to the introduction, that when we were looking at what is reality, what is really out there, and that kind of stuff we were discussing. In this simple world, what is really out there is that these are the cells which become 1 or 0 essentially, and that is about it. This whole world is full of cells, and each cell can be 1 or 0, and they follow certain rules, whether to remain 1 or 0 in the next time cycle. But in this world, suddenly we see patterns like this. This is called the glider gun, and this is a very old game. Game of life was invented in some 60s or something like that essentially, or maybe 70s. So, if you just search game of life or glider gun on the web, you will probably get to see an animation of this. So, this looks like a creature now, of this shape which is moving around. Of course, we are also like that in some sense, made up of how many 10 raised to something, I had mentioned 28 or something simple cells moving around in a unison, pretending to be a creature. But that is the whole idea of emergent systems essentially, that you put together simple cells or simple components and put which obey certain local rules. Each cell only looks at its only neighborhood, it does not see anything beyond its immediate neighborhood, and that its fate is decided based on that essentially. You put in such local rules and build a world like this, and you will find that patterns, I mean because we tend to think of them as patterns, emerge essentially. So, basically combinations of simple things tend to behave in a more complex way essentially. So, more recently there has been a lot of interest, and now imagine that instead of being these very simple creatures that these cells are, which only look at the neighborhood and decide whether to die or not to die, they were slightly more complex creatures. For example, they could have a little bit of a memory of their own, and they could do a little bit of reasoning something. Then we sort of call them as populations of agents, or some people call them as multi agent, and you are talking about simulations here. So, a lot of people, for example, social scientists are looking at these multi agent worlds in which they put together these simple agents and they study the behavior of those simple. Of course, they put together the rules and so on. So, for example, overcrowding rules or things like that, and sort of look at more sophisticated implementations of this. So, I would there is a language called NetLogo. So, you must have heard about Logo, of course, devised by Papert long time ago to teach programming to children. So, there is a turtle which you can say go move north or move west and so on, so many steps or turn by so many steps and that kind of thing. This NetLogo is a more sophisticated language. It has been implemented by some people in the Northwestern University in the US, and it is available freely online. And I have some friends who are sort of working with this and trying to implement these agent based simulations. And so, this whole idea of exploration is to put together simple elements, impose rules upon them, and then study the behavior. So, people have studied, for example, crowd behaviors, and one of my friends who works in TCS in Pune, he has been doing this sort of a thing, and he sort of simulated this behavior of this crowd. So, there was this fire in some restaurant in Brazil or somewhere, and the crowd behavior, he could replicate that crowd behavior by imposing very simple rules on the agents essentially. So, what do you do if you are in a restaurant or a bar and there is a fire in one corner of the room? What would you do essentially, you know? So, to impose simple rules upon them, and then you can actually study the behavior of a crowd essentially. And nowadays, of course, crowd behavior is of great interest, especially in situations like you know, this Uttarakhand tragedy or any tragedy that befalls upon this. We want to see how the crowd would behave essentially. So, there is one direction to this population based system is this agent based simulation. You create simple agents, put them together in a world, and then simulate or run the world to see what kind of behavior would emerge essentially. But we will come back to our genetic algorithms. Which is also a little bit like that, except that there is no spatial connotation. Here we have a space which is made up of grids and cells in which the people live, but in GAs we just have a population and we do not really talk about space essentially, though there have been people who have also started speaking about spatial distribution of populations essentially. So, just as human populations are sort of distributed in different continents and different countries and so on and so forth, they have tried to see whether, you know, the whole population can be partitioned into some sub populations, and evolution basically interaction, mating for example, happens only within that population and not outside this population. And then they try to impose rules like migration. When is the agent allowed to migrate to a new country, if I may use the word? Under what conditions will this migration be successful, under what conditions will it fail, and that kind of a thing essentially. So, for those of you who have been following Australian news and elections are coming up, they have been taking a very strict stand against emigration. So, they have said that anybody who arrives by boat will never be given Australian citizenship essentially, you know. So, rules like this, and you can see how it will affect the population and things like that. But we work with simpler notions, which is that we just have a collection of populations, and what is the algorithm that we had talked about? The first step is selection. So, we have this population of some elements and they are allowed to reproduce themselves based on some fitness value, something like this. That is the first step, which is selection, and we had said that we will implement a roulette wheel kind of a mechanism. Of course, you have to work out how to do that, which will tell which element gets to reproduce. So, if there are n elements, we will spin the wheel n times, and whichever element comes in front of, let us say, the pointer, we will get to reproduce essentially. Then crossover, which basically means that we randomly pair the new population that we have. So, let me draw this by squares. We randomly pair them. So, for example, we could say we pair this one with this one, this one with this one, this one with this one. Okay, maybe I should have had an even number, but still we do random pairings and allow the crossover operator, which is basically mixing up the genes of the two parents and producing two new children. So, you can sort of see this as a parallel search in the same space, solution space, except that we start with a move is made up by somehow selecting two parents and then generating two new children out of it. Instead of one parent giving rise to one child, like for example, in hill climbing or simulated annealing, here two parents give rise to two children in this example. And then we had said mutation, which is kind of a rare event. Once in a while you change some gene randomly essentially. This is meant to take care of the fact that some genes may get lost and so on and so forth essentially. So, let me take an example to sort of illustrate how genetic algorithms work, and then we will come back to discussing what are the issues that you have to decide upon when you are using genetic algorithms for optimization. So, this is an example which I am taking from this book by Goldberg. So, remember I had told you that the genetic algorithms were devised by somebody called Holland, John Holland, and his student called David Goldberg has written this very popular book on genetic algorithms, and this is basically from the first chapter, which is the introduction chapter of his book, and it is a nice example and I like it because it illustrates the whole idea of GA quite nicely. So, it is got a very small population of size 4. So, we have these 4 elements. Okay, so, remember that the first thing we want to do is to encode this. So, when we want to use a GA to solve some optimization problem, we have to first encode the candidate solution, then we have to devise an evaluation function which will look at a candidate and give us a number, and ideally the evaluation function should be in sync with what we really want to do, which means that for the optimal solution the evaluation function must have the highest value essentially. So, let us assume that we will do that. And then the genetic algorithm thing comes into play. Now, in this very simple world, I have a 5-bit vector, and so the four elements that I have in this example are okay. So, I have a small population of size 4, and these are the 4 candidates represented as bit strings, and let us say that we we interpret them as binary numbers, which means that the numbers that we are talking about are, this is 13, this is 24, this is 8 and this is 19. So, essentially these are the candidates, but this is their representation. So, we have these 4 numbers 13, 24, 8 and 19, and we want to Now, our optimization task is to find the largest number that you can represent with 5 bits. Okay, it may sound very trivial to you, but we want to see how genetic algorithms work, and that is our goal, and it is a problem that we understand quite clearly essentially. And so, we have to have this evaluation function, right. So, let us say we decide. So, this f is a fitness function which will take any candidate and give us a value, and just simply let us assume it is x square essentially, a simple fitness function essentially. So, if you were to evaluate these 4 candidates, the values that we will get are 169, 576, 64, 361. Now, what is the role of fitness in our algorithm? Our fitness influences the selection process. The chances of a candidate reproducing itself are proportional to fitness. So, in our roulette wheel, we will have these 4 sectors with areas proportional to these numbers essentially. So, this second candidate will have the largest area, the fourth candidate will have the next largest area, and so on and so forth. So, we will have a roulette wheel like which looks like this, something like this. So, this is 2, this is 1, this is 3, and this is 4. So, we just rotate it, and whichever thing comes here we select that. So, the probability of it reproducing is proportional to the fraction that this is of the sum of this whole thing. So, this probability value is 0.14 for this. So, how did I get these values? Basically, you sum up these 4 numbers, and then this divided by the sum is 0.14, this divided by the sum is 0.49. So, that is how you get the probability values, which means that every time you spin this roulette wheel, the second candidate has about 50% chance of being reproduced, this candidate has about 30% chance, and these 2 candidates have a little less chance essentially, because that is how the areas are divided essentially. So, the expected values, let us call them E, are basically these values multiplied by 4, because we are going to spin the wheel 4 times in our case. So, the number of instances of these candidates that we expect to see is basically 4 times this. So, this turns out to be 0.58, 1.97, So, what are these numbers? These numbers are saying that after I have done this selection phase, and what is the selection phase? I will spin this wheel 4 times, and whichever candidate this arrow points to, I will make a copy of that candidate. So, after I spin it 4 times, I expect to see about 2 candidates of this, about half candidate of this, about 1/5 of this, and 1.25 of this roughly. But of course, in the real world these fractions do not mean anything. In the end I will end up seeing 4 candidates, and let us assume that when we actually carry out this experiment, the values that we get are 1, 2, 0 and 1. It is quite feasible, it is quite possible that if I spin the wheel 4 times, I will get 2 copies of the second candidate, 1 copy of the first, 1 copy of the fourth, and none of the third one. So, let us say this is what happens. This is where the random process is, this is the first place where this random process is showing its effect in the process of producing the next population. So, this population is actually this the one that we have said after we have done the selection phase. We started with this and we end up with this essentially. So, let us redraw that population. So, 0, 1, 1, 1 copy of this, 2 copies of this, and 1 copy of this. So, this is my new population. So, selection phase is over, now begins the crossover phase. So, so let us say we pair this 2 and then we pair this 2 and we put some random crossover point, and we are doing this single point crossover, which means at some point we will break this chromosome into half, and the same point will break the next one into half, and then we will exchange the 2 essentially. So, let us say that our crossover points are like this, one is here and the other one is here. So, this will give us a new population. So, this 0 1 1 0 will come here, followed by a 0, because this 0 comes from the other side. Likewise, this 1 1 0 0 will come here, followed by this 1 which comes from the other side, and similar thing will happen here, 1 1 0 1 1 and 1 0 0 0. So, just to emphasize, I take this part and I take this part and I get this one here, and likewise for the other 4 essentially. So, this is my new population at the end of one round, one cycle of this. So, let us see whether we have a better population to start with. Now, if you look at this average fitness for this, it happens to be 293. And the people who work with genetic algorithms tend to talk about average fitness of this thing, that in general the population is becoming fitter, but of course, we are interested in the most fit element, that is a different point essentially. So, let us see how is the new population. So, these numbers correspond to 12, 25, 27 and 16, and their f of x, which is equal to x square, corresponds to 144, 625, 729, 256. So, the first thing is that average for this new population is 439. So, starting with this average of 293, we have gone through one cycle of reproduction and mating and crossover, and we have got a new population which is this. So, we started with this whose average fitness was 293, and we ended up with this whose average fitness is 439 essentially. So, this is the kind of thing which GAs are looking for, that can we get fitter populations and so on essentially. So, the whole idea is that if you have some function in which you are trying to optimize, then initially your population may be decreased, sort of spread over this whole domain, where this is a, let us say, one dimensional domain, but after you have run the GA sufficient number of times, you will find that the population is kind of concentrated towards the peaks, and one of them hopefully is the solution that you are looking for essentially. So, that is a general idea behind genetic algorithms. So, let us look at this next population, and what would happen in the second cycle. We will not repeat it, but we will just start thinking about it essentially. So, we look at the probability. Again, if you remember, the probability is obtained by taking the sum of all these 4 numbers, and if I 144 divided by the sum would give me the probability of this one showing up in this ruler wheel. The ruler wheel has changed now. So, this happens to be 0.08, this happens to be 0.35, this happens to be 0.26. So, these are the 4 probabilities values, and corresponding to them the expected values, which is basically 4 times this number, is 0.32, 1.4, So, these are the values. So, I want you to now inspect this new population. So, we started with one population whose characteristics are given here. Average fitness is 293 and this has the expected number of clonings allowed. Here also you can see the expected number would be, I mean these are the expected numbers, sorry, 1.97, 0.22, 1.23 and so on, and those are the expected numbers here, 0.32, 1.4, 1.66, 0.58. So, I wanted to look at this new population and its fitness values and make some observations. Well, average fitness has gone up, as you can see it has become 439. The maximum fitness here was 576 and there it is 729. So, that is also gone up. So, is there any problem? What will happen if I continue this cycle? Will I get, what is the solution that I am looking for? 5 ones. So, if I run this algorithm, let us say for 100 cycles, what does the intuition say? Will I get that or not? Yeah. Yeah. Exactly. Now, if you look at the expected values of these 4 elements, these are the 4 elements I have, and the expected values are 0.32 for the first one, 1.4 for the second one, 1.66 for the third one, and 0.58 for the second one. So, it is very likely that when I do this random spinning of the roulette wheel and produce 4 new candidates out of 4 copies of some 4 of these, it is very likely that this first candidate is going to be left out. Yeah, why? Because its expected value, its probability is only 0.08, and if I spin it 4 times, my expected value is 0.32 essentially. Notice that if I were to spin it 100 times, its value would, expected value would go up, but that would amount to saying that these 4 candidates are being cloned 100 times. We are not doing that. We are assuming here that the population remains constant, that we start with these 4 candidates and clone 4 new candidates out of them. And if I do that based on their fitness values, it is very likely that the first candidate will get left out. And as he pointed out, this is the only candidate of these 3 which has a 1 in the middle place essentially, the third bit essentially. So, if I were to remove this, so let us say I were to take 2 copies of this, 1 copy of this and 1 copy of this, then no matter what future churning that I do with this, I will never be able to get the middle bit as 1. So, I like this example because it illustrates exactly this point. Now, what is the remedy to this? Why is this happening? How can we try to see that this does not happen? Go back to nature if you want to.
Variety in the genetics, variety will become more and more uniform as you keep changing.
When will they become more and more uniform? What you are saying has a point, that yes, it is possible that for a given species. So, let us call it a species. So, since we are talking about nature as well. So, if you take for example, the cheetah. Now, the cheetah, if a biologist were to look at it, is, and if you want to call it a machine, is a perfectly designed machine for hunting. It can, in fact, you get to see car ads which kind of try to portray them as cheetahs and stuff like that, and the reason for that is that they can accelerate very fast and they can attain very high speeds, which is good for hunting essentially. Now, the cheetah was such a good predator such a good hunting machine that they all became similar. In a sense, this capacity to run very fast and catch prey came in all. So, the diversity in the cheetah population became less and less and less, and if the diversity becomes less, it means your tendency to explore the space decreases essentially, which is what is happening with this here. If we are getting one candidate without the middle gene, then you can never look at solutions which have the middle gene essentially. So, likewise if you lose some things, then you become rigid in your genetic makeup, which has happened to the cheetah, and which is one of the reasons that since humankind has changed the world so much that cheetahs do not have these open spaces in which they can go and catch their prey, they are under danger of becoming extinct essentially. Just like this particular creature is, or the gene which this creature is carrying is likely to become extinct in the next round essentially. But the question that we want to ask is, what lesson should we learn when we devise GAs? So, when we devise genetic algorithms, what are the parameters that we have to select? The first of course is, how do we encode the solution? Encoding the solution should be done. So, encoding followed by evaluation, these are the first two steps. How do you encode your candidate solution, and secondly, how do you, what is the fitness function that you devise for that essentially. Now, remember that this fitness function will have to be computed for the entire population. So, one of the places where I was reading about genetic algorithms, they said that imagine that you are trying to devise a neural network for pattern recognition. So, you want to recognize some patterns, let us say handwritten characters or something like that essentially. And if you have a training set of 1000 patterns given to you, based on which you are training the neural network, and your task is to identify the parameters of the neural network, which basically means a number of nodes and the edge weights and that kind of stuff. What is the fitness function you could use? One fitness function you could use is that you could test the candidate, and the candidate in this case is a design of a neural network or a neural network on the 1000 training candidates that are given to you, and the fitness value is the number of candidates this network correctly classifies. Now, if you were to devise such a training, such a fitness function, you can imagine the amount of work the generic algorithm has to do simply to evaluate the fitness value of a candidate. In our example, it is very simple, we just compute f is equal to x square, it is easy to do it on the board, but it is not a problem that is hard to solve anyway essentially. If you want to look at more difficult problems, then you have to be very careful in how do you encode the candidates first, and in the next class we will come back to TSP, how to solve TSPs using genetic algorithms, then how to devise a good fitness function. The fitness function should reflect what you want to achieve, because in the way that we have built our algorithm, it is a fitness function which dominates this selection process, that this process of cloning one population into the next and the number of copies you make are dependent directly upon the fitness function. So, the fitness function, if it is good, it will do a good job for you essentially, but there is still one more parameter to be decided, and that is now randomization is a built in process. Randomization takes place here in the selection, in the spinning of this roulette wheel, and the other place it takes place is in deciding this crossover point here. Where do we do a crossover? Maybe it can be done in some more informed fashion, and people have tried out all kinds of things, but we want to look at general purpose algorithms at this moment.
Sir,
the third thing,
how do you decide crossovers? I mean,
yeah. So, I will take your question to mean how do you decide what is the crossover operator essentially. Okay, so, in this case, now if you think about a simple situation like this, where the solution is a bit string, then crossover essentially will mix up bit strings essentially, and without loss of generality a single point crossover will do like any other crossover might have done. Though as I said in the last class, Goldberg has investigated as to what if there is a sequences of characters which somehow provide a good feature, how can we try to see whether they stay together, but we will not get into that. So, we will assume that a simple single point crossover does the job for us, and this point is decided randomly at runtime, whether it is done here or whether it is done here is decided randomly at runtime. So, that is the second aspect of random behavior that is happening here. One is in the roulette wheel spinning and the second is in deciding where the crossover happens. But looking at this example, there is a third thing which should come to mind, which is crucial for the success of genetic algorithms. You should take care of extinction. So, how do you do that? So, somebody had said diversity. How do you increase diversity?
Keep the best people. Increase the
No,
population.
you are looking at it from a wrong perspective.
All the features should be maintained to the next level.
No, no, listen, we are trying to design a genetic algorithm. We are not trying to design the selection or the mating process right now. What is the third parameter in designing genetic algorithms which is going to play a critical role here? The size of the population. Genetic algorithms will work if the population size is large. If the population is large, then they will have all kinds of characters inside their population with carrying all kinds of genes, and they will all have a chance to reproduce in some sense essentially. Now, which is one of the reasons why we have this third phase, which is mutation. For the sake of completeness, there is hope that this mutation process will sometime toggle the middle bit here and we will get going essentially, but in general you have to choose a large population size for this to work essentially. One more aspect that we discussed in the last class, we have not mentioned it now, is as to, so some people have done it as follows, that you have a population of some size, then you take the most fit members, let us say k most fit members. So, this is k, this is n. So, if you have n members, you take the most k fit members, only allow those k fit members to reproduce and mix up the genes, both the processes selection and crossover. So, you get a new population of k elements. Now, take this whole population here. Okay, so what am I saying, that these k elements get to reproduce, which means they die in some sense. Okay, in the process of reproduction that we have, these two parents vanish from the scene and instead these new children come in essentially. So, we get this new children here, k new children, plus we take all this. So, this is k and this is n. So, you have k plus n elements and then you mix them up and take the best k out of this, best n out of this. What we have done here is that we are not keeping the original population at all. Here we have said we will just replace the new one. So, you started with this population and you ended up with this population. In the process we lost the, no sorry, this population after crossover. So, we started with this one and we ended up with this, and none of them are reproduced there essentially. So, we ended up with a new population, which means we replace the entire old population with this new population. But I had said earlier also that it is not necessary that you replace the entire old population, you may want to keep some of the best ones from the old population into the new one, and this is one approach that people take. They say only allow the best people to reproduce, then take the new children plus the old population and from that choose the best 10, and that is the new population, which gives a chance for good solutions to survive in this case essentially. Okay. So, I will stop here, and in the next class we want to come back to genetic algorithms and look at how to solve the travelling salesman problem, how to devise crossover operations for the travelling salesman problems, and what is the representation that you can choose for representing the TSP candidate essentially. So, we will stop here.